We've looked both at gravitational field strength and Newton's law of gravitation. We're now going to tie the two together, and so we're coming back again to look at gravitational field strength. Just to reiterate what you've seen in an earlier video, gravitational field strength, you can consider it to be the force per unit mass, and the equation that we saw for that was that G was equal to the force on the mass divided by that mass, so F over m being the gravitational field strength. But from Newton's law of gravitation, we can do something with that. So in considering that law of gravitation, we know that the force that exists between two masses is given by the equation F, which is equal to G, the universal gravitational constant, multiplied by the two masses, m being usually considered the larger mass and lowercase m the smaller mass, divided by the square of the distance between the two masses. But you can see there we've got, in both equations, we've got F and lowercase m. Down here we've got an F and we've got a lowercase m over here as well. So we can combine, or manipulate this Newton's law of gravitation, and instead we're going to write F over m. So basically dividing both sides by m, and we end up with an equation G capital M on r squared. So that means that we've actually got another equation for gravitation. Considering that F over m is equal to gravitational field strength, we can then write that that's equal to G times the mass of the object that is being considered divided by the square of the distance between them. So that's an important equation there. That's in the data booklet. So that basically now tells us the gravitational field strength at any distance around a mass. So I'll just notate this really quickly. So the value of G is the gravitational field strength. And you'll also recall that we can use a different term. We'll just mention the units here. The units of gravitational field strength would be newtons per kilogram, or it could be considered to be gravitational acceleration. And the units there would be meters per second squared. So either of those two units for the G. Capital G, as we've already seen, is the universal gravitational constant. And that has a particular value, given that it is a constant, and it has the value of 6.67 by 10 to the negative 11 Newton meters squared per kilogram squared. Now that's a constant value that will be given to you in the data booklet, so it's not one that you have to memorize. M is the mass of the object around which we are interested. So it might be, say, the Earth or the Sun. That's measured in kilograms, and R is the distance from the center of mass of that object. So note that we're always looking for the distance from the center, and not just, say, the height above its surface. And the distance from the object center of mass will be in meters. So just one more note to make about this equation. If you think about those two quantities, we're really treating both masses m and lowercase m for that matter as point masses. Now what we mean by a point mass, a few different ways that you can think about it. The way that I'm going to explain it is that the size of the mass doesn't matter. And by size, I mean sort of the radius or the volume. So we're just looking at the size of the mass isn't particularly relevant. Now, in the case of planets or stars, obviously the size of the planet or star, size obviously does matter in that case. So we do need to be aware of the fact that planets and stars have a certain distance. However, if we have that the radius, so the distance, if the value of r is greater than the radius of the star or planet, then that equation will actually still work. When the distance between the point of interest and the center of mass of the object, when that's larger than the radius of the object, then this equation still applies. So we're basically looking at the gravitational field strength outside a sphere. If you were to consider inside a sphere, so inside, say, a star or a planet, this equation doesn't work. And if you think about it, the further you get into a star or a planet, you've now actually got more mass above that particular point, and so the mass is no longer a point mass. The size does matter, and so the gravitational field strength will vary as a result. In the next video, we'll then link these ideas of gravitation with circular motion from 6.1 to draw this unit to a close.